Right, Assalamu alaikum and good morning, everyone. I hope everyone is doing great today. So, in this recorded lecture, I will share with you the content or the topic that we have not managed to cover before the mid-sem break, which is on the PN junction under illuminated condition. Okay. So, as usual, before you start to learn about this topic, I want you to be able to recap on what you have learned last time. So, for example, in this particular case, try to have a look at these three questions and try to explain to yourself and to your peers uh, about your understanding on these three subjects. Right. For example, the first one in a typical PN junction. Describe what happens to electrons and holes during forward bias condition and reverse bias conditions. So we have discussed about this topic when we talk about PN junction under three different biasing conditions. The first one is zero bias, or essentially is at thermal equilibrium. And the second one is when the junction is forward bias, when you connect your P side of the semiconductor material to the positive polarity and N side to the negative in order to create a forward biasing. On the other hand, the third one is called reverse bias, where you connect your P side of the semiconductor to negative polarity and the N side of the negative or of your semiconductor to the positive polarity, and then you start biasing the circuit. And that's where you start to have your reverse bias conditions. So in these three different conditions, you should be able to describe what happens to the flow of your carriers, electrons and holes, the change of barrier heights and the diffusion and whatnot, right? So the second question here suggests one way to improve J naught in a diode. So remember last time we've discussed about J naught being reverse saturation current density, or we also call J naught as leakage current, right? So try to recap the equation that that involves J naught, and how do we then minimize J naught in our PN junction or in our diode, right? And the last one, name two physical mechanisms that give rise to PN junction breakdown during reverse biasing condition. So you have to go back and try to describe the two physical mechanisms. What are the details? How big is the reverse bias voltage required, for example, in order to cause a breakdown, and what are other conditions required in your diode in order to enable these conditions, okay? So these are the three main things, or the G's of the previous topics, PN junction and the biasing, that you should be able to understand and describe before we move on to PN junction under illuminated condition. So in this topic, we are going to review PN junction with illumination, or PN junction under illuminated condition. So essentially what we're going to do here is you are going to start off with your PN junction at thermal equilibrium. Last time, remember when I told you when you want to compare whether you're doing biasing, forward or reverse, or giving illumination to your junction, you always have to go back to your thermal equilibrium condition. So you should be able to describe what are the conditions, how does the band diagram looks like, how do you demonstrate or illustrate the barrier height before you start discussing about applying external sources or external agents to your system, lights or electric field or something. So in this case, you should be able to describe what are the conditions obtained or achieved at PN junction at thermal equilibrium first. Then only you can describe PN junction under illumination. So we have also discussed last time about carrier injection, right? When we compared the change will only be seen in minority carrier but not in majority carrier, because majority will remain the same, especially when you're talking about low injection condition, right? And the condition will differ, of course, when you talk about high injection level. But when you talk about low injection level, for example, in the range of 10 to the 12, um, when you're talking about your silicon with, say, p-type of 10 to the 19, for example, so obviously you won't be able to see any change when you compare your minority carrier at 10 to the 12, sorry, the injection level at 10 to the 12 with a 10 to the 19 of your doping level, right? So 10 to the 12 will just be negligible. But however, if you're talking about 10 to the 19 for your majority or for your doping level, so your minority will then be about 10 to the 1 if you go back to law of mass action, right? N times P equals to NS squared. So your minority will just be around 10 to the 1. And of course, in this particular condition, 10 to the 12 will dominate 10 to the 1. And in this particular condition, your minority carrier, the level of minority carrier will change because of the injection level, right? So under illumination, free charge carriers are created by the absorption of light. So since we're talking about illuminated PN junction, so we're talking about absorption of light. And we've also discussed, you have to recall the absorption coefficient, the absorption depth, right, for a range of different semiconductor materials, for indirect, for direct band gaps, all those. And those three conditions are when the EPH, the incident of the energy of the incident photon, is less than the EG, the band gap, where the light will not be absorbed and there will not be any generation of charge carriers. And the remaining two conditions are the conditions that will cause generation of the free charge carriers, where the first one is EPH equals to EG, right? The energy of the incident photon is equal to the band gap of your semiconductor material. If you're talking about silicon, crystalline silicon, then we're talking about 1.12 electron volt. And the light will be absorbed, and therefore the charge carriers will be generated. And the third condition can also cause this creation of photogeneration, where your EPH is more than the EG, where we learned last time that the light will be absorbed, and the valence band electrons will be excited into the conduction band, but not just into the conduction band, but further up into the CB. And then you're going to expect thermalization to occur instantly, right? So the free charge carriers are collected by the depletion region, giving rise to light generated carrier density. So to be able to have your light generated current density, or to be able to generate photocurrent, we call it photocurrent because it's due to photo generation process. So remember last time we talked about photo generation is actually one word, photo generation or photo current. So this photo means it's due to absorption of photons, right, or just absorption of light. So in this case, to be able to generate light generated current density, so the carriers generated within the PN junction need to be collected. So how do we then collect the carriers? So later on in your second part, in the devices, you're going to see, for example, if you talk about solar cells, which is based on this principle, absorption of light and generation of photo carriers, generation of photocurrent, and you're going to expect IV curve at the end. You're going to see later on that to be able to complete the circuit, the carriers need to be collected by the junction. So for example, if you talk about left being p-type, right being n-type, so if you have generation of electron and hole pairs, in the n-type region, for example, so you want to collect the hole into the p-type, right? You want to collect the hole into the p-type, and you want to collect the electron in the n-type. Okay, so what has to happen then, for example, if you talk about collection of hole into the blue region, p-type, So we have learned last time that we have a space charge region within the depletion region. So negative on the left hand side because of its p-type semiconductor, and positive on the right hand side. And this hole needs to be collected by the junction. Okay, so it's going to be drifted and then it's going to be swept, which as if you hold the hole and then you tarik masuk to the other side, right? So the hole is going to be swept into the p-type, where the hole becomes majority carriers. Okay, so the moment it's generated, it is just a minority carrier, so it will diffuse and it will be drifted across the space charge, and it will just be collected into the p-type. So the moment it gets into the p-type, the hole is now a majority carrier. Okay, the hole is now becomes majority carrier. So this mechanism is called carrier collection. So it's called carrier collection. And we assume that there is no recombination happening within this depletion region. So that means as long as the hole crosses the junction, the ACR or the depletion region, there's no recombination in this region, and we can just assume that the hole is collected into the p-type, right? And the same thing happens to electron as well. So if you have photo generation of your electron hole pass in the p-type, the electron needs to travel and needs to cross the p-n junction region in order to be collected into the n-type region in order to complete the circuit. So during the actual operation, the two processes, these two processes that we're going to see later on are dependent on principle of superposition, which is driven by dark current and light current. Okay, dark current, if you go back here, will follow this injection, diffusion, recombination, and drift phenomena, right? Phenomena, whereas, and this dark current will eventually create the leakage current, J naught. Okay, the light current, on the other hand, follows drift, generation, diffusion, and collection phenomena or the sequence, and this will contribute to JL, light generated current. So we're going to see later on how are these two J's, J naught and JL, are correlated to each other. So last time when we talk about PN junction under thermal equilibrium, we have learned that in order to achieve thermal equilibrium, the diffusion of carriers need to happen from both sides of the PN junction. So assuming my left hand is p-type silicon and my right hand is n-type silicon. So you have your holes as a majority carriers here, electron as a minority carriers. On the right hand side, n-type electrons as minority carriers, majority carriers, hole as the minority carriers. So the moment you put them together as a p-n junction, you should expect diffusion of the majority carriers, holes into n-type, electrons into p-type, and this transport phenomena will cause creation of depletion region, right? Consists of fixed charges, a negative fixed charges on the p side, positive fixed charges on the n side, and formation very high that will stop further diffusion of your carriers into the opposite side. And at that point, you're going to have your VBI, you're going to have your Berry height, which is QVBI, and also most importantly, when you achieve the thermal equilibrium condition, you are going to have only a single Fermi level, right? Remember last time we talked about bringing two levels of Fermi energies. For example, if you talk about P side, then we're talking about your EF being closer to valence band on the P side, and then on the N side, originally your Fermi level is closer to your conduction band. But the moment we have achieved thermal equilibrium condition, there will only be a single Fermi level, right? So you can label this as EF in the P, EFP, EF in the N, EFN. But bottom line, there is only one EF at thermal equilibrium condition. So when you want to talk about illuminated junction, so remember I always told you to go back to thermal equilibrium condition where you only have a single Fermi level obtained the moment your thermal equilibrium condition is achieved. So when you then illuminate your junction, which is already at thermal equilibrium, you are now creating a gradient in a minority carrier quasi-Fermi level, right? So it used to be like that on the F side or on the P side, sorry. The moment you say you're shining photons, kat sini it can be that, can be there somewhere. You're illuminating your PN junction photon, assuming this has EPH of equal to, or perhaps some with EPH more than, where both will cause absorption of light, right? Absorption of light, as we learned last time when we talk about absorption in generation, right? Generation and recombination topic. So this act of illuminating your junction with photons of this energy spectrum will cause gradient in the minority carrier for quasi-Fermi level here, EF, right? So remember on the P side, your electrons are the minority carriers. And here we're talking about minority carriers since minority carriers will be affected during the injection condition. So forcing this electron to flow to the right. So since you have got your gradient in minority carrier on the P side, so it will force the electron to flow to the right. So action number 2, right? This number 2 is due to the movement of electrons to the right into the n-type region. So remember this central part is your depletion region. I'll just write here as W or depletion region or SCR, same thing. So where they need to cross, where they need to be swept into the opposite region, which then they now become majority carriers, right? So at this point, if the diode is short-circuited, so that means if you connect your terminal on the P side, on the N side by a wire, so electrons will flow through the external wire, action number 3 here, and recombine with hole on this side. I recombine with hole on this side. Finally, a hole in the VB or the valence band moves to the left, action number 5, and replaces the lost hole, right? So this is under short circuit condition where you don't have any load connected at the outer circuit. On the other hand, if you connect a load ini could be anything yang ada resistance. So it could be, if you're talking about the real system, for example, solar cell, you're connecting across perhaps a device, right? A phone or a calculator or a TV or something, depending on the load capacity. So under illumination, the diode will become forward biased due to the light. The total current can then be considered as the superposition between your IL or JL essentially, which flows in reverse direction in diode voltage dependent dark current. So it's going to be related to JL and J0 eventually. You can also represent this as IL and I0, depending on what you are trying to say. So if you're talking about J, then we're talking about current density, photo generated current density. This I, on the other hand, is not it's just a current, photo generated current, but it's not over cm squared. But the first one, if we're talking about milliamp, then it's going to be over cm squared. But for IL, it's just milliamp without cm squared, right? But you can represent either in the form of J or in the form of I for both cases, right? So this is what we learned last time on the continuity equation, where we learned about this generation minus recombination rate. And we've also covered the equation on the general solution, which is given by this equation, right? So let me just go through the equation, right? Right, okay. This current in the quasi-neutral region. So remember last time when we talk about your PN junction, say this is the P side, this is the N side, this is the W. So remember last time that we talked about, we learned that only this region has space charge, right? Space charge region. It's called space charge region. But all the regions outside the SCR, outside the depletion region, is called QNR, quasi-neutral region, which retains the the polarity or the condition of the original PN semiconductor materials as you go away from the junction, right? So since the carriers, electrons and holes, need to travel through both Q and R's, so we need to know how do we then calculate the currents through the Q and R, quasi-neutral region. And this is the equation that governs the current, right? So it's Q times diffusivity times your whole the density neglecting the combination in this region by including the effect of large energy carriers. The change in carrier density across the depletion region is given by Q times generation rate times W, assuming there's no recombination in the depletion region, right? So then the J will be given by J naught times e to the power of QV over NKT, and this N is the ideality factor of the diode. So this goes back to the diode equation like we learned last time, ideality factor. So ideally, you want your diode to have ideality factor of 1, ideal. But in the real case where you do your fabrication and the measurement, it won't be 1. Okay, you won't get 1. So J naught retains the value of the dark. So J naught being the saturation, reverse saturation current density, or dark current. We call that dark current density. So remember last time we discussed that you want to minimize J naught, right? You want to maximize JL, you want to minimize J naught. Minimize J naught, you want to maximize JL in order to produce maximum photocurrent from your diode, right? So JL is given by this equation, Q times generation rate times your LE, diffusion length of electron, plus the width of the depletion region, plus this is distance dimension, right? Distance in dimension. So plus diffusion length of hole. So this shows that the light generated current JL has a value equal to that expected if all carriers generated by light in the depletion region are collected, right, with a minority carrier diffusion length on either side were to contribute. So this means they are collected. So if they are not collected, on the other hand, they will not be able to contribute to JL. Okay, maknanya you punya carrier tak sampai, tak cross lah, that is not collected by the junction, so it will not contribute to the current density eventually. And you can illustrate this equation by this, your P and N on both sides, and then the W in the center, and the diffusion length of both carriers. So simple physical interpretation of JL, assuming minority carrier efficiency is 100% in the central part. But in the actual case, it will not be the case even in the depletion region. But for now, let's just assume that depletion region A to B still has the perfect collection probability. Here 1 means 100% carrier collection, yeah? So you can either represent your collection probability in percentage. So that means this equals to 100%. So this spans from 0 to 100%, for example, or you can also represent that as 0 to 1. Either one is fine, as long as you are consistent in giving the description. So the actual collection probability of light generated minority carriers, okay? The probability of collection of light generated minority carriers is unity. So that means it's unity equals to 1 equals to 100% if the electron hole pair is generated in the depletion region. So if your photo generation takes place in the depletion region, you can assume that the carriers will be collected 100%. This is the sketch of photo generation. The moment the light is absorbed by the semiconductor and the valence band electron is excited into conduction band, then so this generation process is this creation of electron hole pairs, as we discussed last time. And if this happens within the material, within the central part, you might want to sketch this as a PN junction as well, for example, so that you can get a better picture. Okay, so P on the left and on the right. So this is the depletion region in the center. So if the light generates electron hole pairs in the central part, you can assume that the collection probability is 100%, right? But this collection probability falls off exponentially if you go away from the depletion region. Okay, so that means if you're going away from the depletion region to the right or to the left, so you're going to expect, you should expect your collection probability to fall off by this factor, right? For electrons and for holes on both sides. So the decay constant of this fall off is the minority carrier diffusion length. So it will be dependent on LE and LH. And this is also related to the previous equation that we learned in recombination, where your L is equal to square root of d tau, right? Diffusivity times carrier lifetime. And we've also learned from the previous topic that from this equation, we know that L is proportional to tau. That's why when you are given a wafer, for example, to check on the quality, you can do a lifetime measurement, minority carrier lifetime measurement, and from there you should be able to tell the quality of the diffusion length expected in the device eventually by this correlation. L is proportional to tau, and L is equal to square root of d times tau. So if you have a very low minority carrier lifetime, then you should expect that diffusion length is very low. And eventually, you can relate that to collection probability in the device as well. So that means if you start off with a very low minority carrier lifetime, you should expect your collection probability to be very low, right? Minority carrier lifetime leading to diffusion length, leading to collection probability. So low here means low here as well. On the other hand, if you start off with a very high carrier lifetime, you should expect high diffusion length in the device and high collection probability, and therefore your JL will be high as well. So that's how you should see the sequence or the correlation of how the collection probability affects the device performance. So you're going to see this part more clearly if you talk about PN junction, solar cell later on, yeah? So since illuminated junction is very related to solar cells, so we can actually use this principle, this collection probability principle, in order to design our solar cell. So for this particular slide, I'm just going to show you how the principle of collection probability and the diffusion length and so on and so forth can help in designing the junction location in your solar cell. So we have learned all this while that typically if you have a solar cell of say 180 micron thick silicon wafer, crystalline silicon, your junction depth is this, yeah, where you have say your wafer is p-type, you need to diffuse a very thin layer of n-type. So this depth of n-type is called junction depth, xj. So xj, we're going to learn this xj more in the next course, ZAT387. How do you calculate, what are the factors affecting the xj and stuff? So in principle, this is the junction depth, and this is the junction that we are talking about here. How do you then place the depth of this junction? Do you want to go at this depth? Do you want to go at this depth? Do you want to go very deep into the wafer, for example? So how do you go about designing the junction location in the wafer so that you can maximize the current collection probability as what we learned in the previous page? So we have seen in a generation topic that photon flux, photon flux within solar cell, within semiconductor material, falls off exponentially, right? So we've seen that. Remember last time we talked about 1 over E, where the intensity of the light drops to about 36%, and that is called the depth of absorption. So the photon flux falls off exponentially within increasing distance. So that means if you say this is x is at 0, so as you go further into the crystalline silicon wafer or some other semiconductor materials, you should expect the photon flux to reduce in terms of its intensity. And as a result of this, since a photo generation of carriers is proportional to the photon flux intensity, so therefore Gx is strongly peaked at the surface. So your Gx is the highest at the surface, okay? Because your photon flux is the highest at the surface as well. So that's how it goes. So you can represent this as this curve, right? If you see collection probability on the y and photo generation is also on the y, two parameters on the y-axis, and x being the distance into the crystalline silicon or into some other semiconductor materials. And A and B here on the x is the width of depletion region. So the Gx will then be giving this profile, since it is a peak at the surface. You should expect as you go into your semiconductor material. And at the same time, we have learned in the previous page that typically the collection probability takes this shape, right? It's going to be a decay exponentially away from the junction, and then it's going to be a unity within the junction, within the depletion region, and it's going to fall off as well on the other side, just like the way it falls off on the previous side, on the left-hand side. So putting this into the very same graph, you should expect that, right? The very same thing. And to know your current, the current generated, essentially JL, I'll come back to this JSC. Essentially, JL will be dependent on both photo generation rate, Gx, and then at the same time, the collection probability together. It's like you superpose the two things together, Gx and your collection probability. And if you're about to design two types of junction depth, so one is a bit closer to the surface because the X is quite small in that sense, while the other device has a deeper junction, right, into the silicon. So maksudnya you can just put it as perhaps your device yang warna merah tadi sampai kat sini, device yang warna hitam, the junction is a bit into the silicon or into some other materials. So this is, let me just put this as red, and the deeper one is black. Okay, so so this will result in the GL, right? Light generated carrier density. But if you talk about solar cell, eventually you're going to learn about this in the second part. As you should expect later on when you plot your electrical characterization of solar cell, it's going to give you a shape like this. Okay, under illumination, right? Illuminated, not dark. Illuminated. The intersection of this curve to the y-axis is called short circuit current, JSC. The intersection of your curve to the x-axis is called VOC, open circuit voltage. So it's JSC and VOC. So coming back to this, JSC is essentially like JL, right? So you should expect maximum JSC to occur when your FCX or your collection probability is close to unity near the surface. So that means the junction needs to be designed to be as close as possible to the surface in order to produce maximum photocurrent at short circuit condition, JSC, short circuit current density, right? So that means if you want to design a junction, say for red, assuming you are doing your junction depth at about 200 nanometer, for black, maybe you're talking about 2 micron, for example, or 2000 nano or 2 micron. So in this case, if you compare 200 nanometer and 2000 nanometer, so obviously your 200 nanometer of junction depth will give you higher photocurrent, right? Higher photocurrent at short circuit or JSC because the junction is designed to be as close as possible to the surface, right? On the other hand, if you go for a very deep junction, then you should expect your carrier collection probability to be very poor because you're essentially bringing that curve into the device, and you should expect the fall off to reach zero before it reaches the surface. So therefore, the collection probability is not ensured, right? So that's why when it comes to the junction design, so if you talk about typical crystalline silicon solar cell in the market right now, we're talking about junction depth of about 200 to 300 nanometer. You don't go to 1 micron, you don't go even to 2 micron, that will make it even worse. So typically it's in the range of 200 to 300 nanometer depending on technology. And you learn here that you want to place your junction as close as possible to the surface, so that is theoretical in nature. The fundamental is that, but at the same time, you don't want to go too near to the surface as well. For example, you might design your first device at 200 nanometer in terms of your depth, but the second one you might want to try at 30 nanometer, for example, and that's very, very close. So if you just learn about this principle in order to do the design of a junction, then you'll probably say 30 nanometer will give you a better JSC. But in principle, if you combine with other design consideration in a typical PN junction for solar cell, there'll be some other factors that will be coming into the equation and affect the results. So at that point, not necessarily 30 or 50 nanometers or 100 nanometers will give you better results than 200 nanometers, right? So this is just the level that you have learned so far, but when it comes to the device design and some of the factors at play, there will be more factors coming into the equation that will determine the optimum junction design, right? So that's why instead of saying 30 nanometers to be better, you wouldn't see that because you need to design a junction to be slightly thick, but not too thick. So there's always an optimum point in that sense, right? Okay. Depletion region effects. Depletion region has been ignored in the analysis of this file. So we have been assuming that we're going to have that kind of carrier collection probability, right? So, and this being your depletion region A and B, and the decay stays on the left and right. So we have been assuming that this is always what? Always 100% in the depletion region. So, however, we should also consider recombination and optical generation within the volume of the depletion region. But in the real case, there will always be recombination in the depletion region as well, and also optical generation within the depletion region as well, right? So we have discussed about this in the depletion region, but we have been assuming that this has always been one, or that means there's no recombination within the depletion region. But in actual case, no. We always have some level of recombination, but usually suppress a lot in the good cells. So the physics are not straightforward and better left of the more advanced course. However, the contribution of recombination in the depletion region results in an additional current. So if you have recombination in the depletion region, is going to contribute to an additional current that flows in parallel to those currents in N-type, NP-type region, in the quasi-neutral regions. And this additional current is given by this saturation current density within the depletion region, JDR equals to J02, which is given by this equation, exponential of QV over 2 kT, because it's not ideal in this case, -1. Okay, you try to have a look at how can you represent this in a diode equivalent circuit. You can look up on the PV CD-ROM, PV education website to know how does it look like on the equivalent circuit when you talk about current due to recombination within depletion region, right? You should be able to represent this current within the diode equation and diode equivalent circuit. Optical generation, the physics here are easy if we assume that if it is assumed that the electric field sweeps are all optically generated carriers before they can recombine. So we have discussed about this equation previously, Q times G times W in the depletion region. Yeah, so I think that's all for this particular topic. So let me just recap before we finish. So essentially in this topic, you learn about PN junction under illuminated condition. There'll be superposition, principal superposition between dark current and light generated current, which will eventually be represented by the equation that we covered just now. So you should be able to describe this illuminated condition, what happens to the gradient and minority carrier Fermi, quasi-Fermi level with respect to thermal equilibrium condition. You should be able to describe the transport of carriers. In this case, electrons flowing from the left to the right into the N-type region to be collected by the depletion region, and eventually it becomes majority carriers on the right-hand side. Okay, and what happens to the PN junction when it is short-circuited, right, which results in JSC eventually, and what happens to the PN junction when it is connected to a load. And then the equation, the boundary condition, and then these two equations incorporating diffusion length, and then how is it related to diode saturation current density, J0, and light generated current density, JL. And then the collection probability away from the junction. You can see the fall off of the collection probability if you go away from the junction. And in this condition, we assume that we have a perfect collection probability within the PN junction depletion region. And we have also learned about the redundancy of the GX, the generation rate, which falls off exponentially into the device, and how that can be correlated to the collection probability that we learned on the previous page, which helps us to design the junction depth of our device. And we have seen that if you compare 200 nanometer of depth with 200 micron at 2 micron of depth or 2000 nanometer, you should expect your device with 200 nanometer to give you better short circuit current density. But this is not necessarily true if you talk about thinner junction depth, because there will be more factors coming into play that you're going to learn eventually in device part on solar cells. And in the real life, you should expect a depletion region to have recombination as well, right? We have been assuming that there's no recombination within the depletion region, but just recombination outside the depletion region. But in the actual case, you should also expect recombination in the depletion region, and the additional current that results from the recombination in the depletion region can be represented by JDR below. Okay, so you should be able to sketch the representation of this JDR or J02, if you like, with the ideality factor of 2 in a diode equivalent circuit, right? How does it look like on diode equivalent circuit? So I guess that's all for this topic. I wish you all the best in the second part of the course with Dr. Marzaini. So if you have questions, just let me know. If you don't understand, just let me know. You can always come to discuss with me if you don't understand any topics from the previous lectures since day one to until the exam break. You're welcome all the time. Just let me know. We can always discuss. Bye-bye. Take care. Assalamualaikum. And stay safe.